here we've got our next test in 2.5 weeks. I am going to definitely do my best to get your take-home tests back to you tomorrow as much as I can. Might not quite be able to reach everybody, but hopefully most of you can get it back by tomorrow, for sure by Thursday, sometime this week here. All right, today we'll focus mostly on well, a little bit about linear approximations, which we really didn't get to in class on Friday, but you did have homework. I hope it went okay. I don't think it was too hard. The new topic we'll do today, called about gradient vectors, is more difficult, and it's sort of more fundamental to everything that we're doing. So you're really going to want to make sure that you're paying attention to all for that. All right, let's do a linear approximation example. The examples you typically get in this feel a little bit phony because we have all this technology, but they do illustrate the ideas of linear approximations. And even though we've got the technology to do them without just thinking about linear approximations, it's still useful ideas in other applications of calculus. But here's your typical kind of example, maybe to estimate the value of some expression where you're plugging in numbers that are close to certain other numbers. For example, maybe you want to evaluate 10.98 to the second power times 2.03 to the third power. Okay, obviously we have technology that can do that in a snap. How they do it before they had the technology to get an accurate answer besides the typical way you learn how to multiply, which you wouldn't want to use if that were, say, a 7th power and an 8th power. Well, what you can do is you can define a function related to the quantities that you see here. For example, x squared times y cubed. That's defining in such a way that we want to estimate this quantity by plugging the numbers into the function. So you're trying to figure out a function that will match that. 2.98 squared times 2.03 to the third power is the same as f of 2.98 comma 2.03. And then you want to use linearization, the derivative, to estimate this quantity. It's difficult to do with the squares and cubes. Again, it would be more difficult if we had higher powers. So we want to come up with a simple function, a linear function, that's going to help us do this estimation more easily. And you take the partial derivatives to help you do it. The partial derivative of z with respect to x, I can label z as the dependent variable here if I like, which you can also call the partial derivative of f with respect to x, is found again by treating the y as a constant. Think of the y as a constant there, you're going to get 2xy cubed. Then the partial of z with respect to y treats the x as a constant. That's just a constant. You've got to bring the 3 down. You're going to get 3x squared y squared. You want to pick numbers that are close to what you see here, such that these things are easy to evaluate. For example, that's close to 3, and that's close to 2. Use those numbers, 3 and 2, to help you find this local linearization. The formula that's in the book that you use goes like this. L of xy, L for linear, is f of AB. The point AB is your particular point that you're focused on. Not equal to this, but the numbers that are close to those. AB for us is going to be 0.3 comma 2. Add on the partial with respect to x. Evaluated at AB. Again, we have this other notation for that partial derivative. Multiply that times the change in x, which is x minus a. And then add on the partial with respect to y, evaluated at a comma b. Multiplied times the change in y, which is y minus b. So there's your general formula for your local linearization of the function f near the point AB. It's a linear function that approximates f well near the point AB. F of xy is approximately L of xy when x, y is approximately AB. So go ahead and plug the numbers in. For this situation here, put them over here. Again, A, B is going to be 3, 2 for us. What's f of 3, 2? That's going to be 3 squared times 2 to the third power. 9 times 8, 72. Plug the point into the derivatives. Partial with respect to x, evaluated at this point, 3, 2, plug it into this formula. 2 times 3 times 2 cubed. 2 to the fourth ultimately is 16 times 3 is going to be 48. And f sub y of 3, 2, that's the partial with respect to y. Look at this formula right there. 3x squared is going to be 3 times 3 squared times y cubed times 2 cubed. You're going to get 27 times 8. Put my head here. I think it's 216. Somebody check that. Oh, it's 2 cubed? Oh, thanks. 2 squared here, right. So that'll be 108. 27 times 4, yeah, that'll be 108. So now plug these numbers into the formula. 72 plus 48 times x minus a again is 3, plus 108 times y minus b is 2. So there's a linear function. X and y just appear to the first power. You can also think of this as delta x, the change in x if you like. Think of this as delta y. In the xy plane, 2.98, 2.03, right around here. The 0.23 itself is right here. Excuse me, 3.2. 3.2 is right there. 2.98, 2.03. There's a little bit above and to the left of it. We're moving the point a tiny bit toward the northwest there. What is the function value at 2.98, 2.03? That's approximately L of 2.98, 2.03, which is fairly easy to find even in your head. 72 plus 48, plug in 2.98 right there. You're going to get negative 0.02. Plug in 2.03 right there, you get positive 0.03. So let me check my work with this, but I think I'm going to get it right. 72 minus 0.96 would be 48 times negative 0.02 plus, what would this be, 3.24. Double check my work. I think that's right. 3.24 minus 0.96, that will be 2.28. That's being added to 72. So it looks like 74.28. Is that right? All right, let's check how close this is to that. You can try with your calculator right now if you like. I'll do it on Mathematica. .98 squared times 2.03 to the third. Hopefully it's close to 74.28. Yes, close. Okay, this is more accurate. This is more of an approximation. It's an underestimate of the true value. What's going on here geometrically, we're using the tangent plane. L has a graph that's the tangent plane to the graph of f near the 0.32. And evidently, since we get a lower value here with L, slightly smaller, that tangent plane must be below the graph. The actual graph is evidently sort of some sort of concave up behavior near that point. All right, so that's the main kind of application we've had. Okay, we'll do more applications. Actually, we can talk about one other kind of application right now, and the application is to hint towards something else. It's more of a theoretical application. You can take this approximate equation that I think I just covered. Okay, f of x is approximately equal to L of xy, where L of xy equals this. And you can subtract f of AB from both sides. And think of that as a change in z. Think of, again, I'll say what I was talking about there. Think about this approximation right there. F is approximately equal to L, where L equals that. Subtract f of AB from both sides. On the left side, f of xy minus f of AB is going to be the change in the output of the function as you change the input a little bit. It's going to be delta z. This can be thought of as delta x. This can be thought of as delta y. And if I use the Leibniz notation for the partial derivatives, I can write this in the following kind of way. Okay, it's understood when you look at something like that you're starting at some point for the input, the point A comma B, and you're letting that point change a little bit. That's understood. In the x direction, you change by delta x. In the y direction, you change by delta y. The total change in the output of the function is approximated by this linear function of delta x and delta y, in effect. That can be thought of as a dot product. This thing right here can be thought of as a dot product. A vector whose components are the partial derivatives, dotted with a vector whose components are the changes in x and the changes in y. In fact, this can be thought of as the change in position, if you like. This can be thought of as a delta r. So, evidently, this vector right there is something special. It is very special. It's got a name. It's called the gradient of f. Remember I said the fact that we call these derivatives, in the multivariable case, partial derivatives, kind of implies maybe there are non-partial derivatives, maybe total derivatives. This, in a sense, is a total derivative of f. It's combining the two partial derivatives. It's got a certain special notation that looks like an upside-down equilateral triangle in front of the f. It's usually not called triangle f. Sometimes people call it df, even though it doesn't look like a d. Sometimes they call it, well, the gradient of f. That's perhaps the safest thing to call it. Some people call it del. But I think the greatest name for this is the name given to it by its originator. I forgot the guy's name, back a couple hundred years ago. He thought it kind of looked like a harp, especially if you draw like an extra line there. And evidently, like in Greek or something, the word for harp is nabla. I just think that's the greatest word, nabla. Okay? He actually got ridiculed by some other mathematician for calling it nabla. It's a little story that's in here, actually. If you want to look at the story, it's on page 813 in the margin. The person who wrote it down was named Tate. And James Maxwell, who was more famous than Tate, kind of joked with Tate, why'd you call that nabla? But I kind of like calling it nabla, so I might call it that sometimes. I'll probably usually just say gradient. It's the gradient of f. It's this vector where the components of the partial derivatives are. And this is one reason it's important. Okay? This is one reason it's important, is you can approximate the change in the output of the function by taking the gradient of the function dotted with the change in the position as a vector. That's an approximation you can write down. What else can you do with the gradient? Lots of things. can use the gradient vector to find something called a directional derivative, which technically speaking, as always in calculus, has a definition based on limits. But I think, at least for the purposes of today's class, I'm going to avoid talking about limits. Let's write it down in words first. The directional derivative of f at a certain point P, whose coordinates are a comma b, in the direction of what? Well, how do you specify directions? You typically specify directions with vectors. And it's going to turn out with directional derivatives, it's best to specify the direction with a unit vector in the direction of some unit vector u, whose components are, say, c and d. So the fact that u is a unit vector means its length is 1. You could also say that the square root of c squared plus d squared is 1, or just, you can get rid of the square root, you can say c squared plus d squared equals 1. What do we want this to represent? We want it to represent the change, or the rate of change, of the function, of the outputs, in the direction specified by u. If we move away from the point a little bit in the direction of u, this is going to measure the instantaneous rate of change of the function. We'll talk about it, what it means graphically in a few minutes. It turns out to equal the gradient of f at p dotted with u. That's what it turns out to equal. It's also got a special notation. Capital D sub u of f evaluated at p. That's the special notation for the directional derivative of f at p. And this is the best way to calculate it. Again, I said a few minutes ago, you can calculate it with limits. In fact, you should define it in terms of limits. But it's a theorem that you end up calculating it this way. Okay? What does it mean geometrically? Let's focus on that now. It's probably best to remind you what we've done so far. Thinking about derivatives geometrically. Here's our function up here. Just a quick review of some things. I want to write down that function again. These two lines calculate the derivatives with respect to x and y. The capital D is the differentiation operator in Mathematica. It calculates the derivative of whatever function is in there before the comma with respect to the variable that's after the comma. So these two things calculate these two derivatives. You should take a few seconds to compare these things with this function and confirm in your head that those are right. I can, if I like, and I will do this, go ahead and use those expressions to define functions representing these partial derivatives that I'm calling fx and fy, not bothering using the subscript notation. And then I can interpret these things geometrically like I showed you last week. For example, we can go down and let's see, I don't remember where I put the code. Right here, I think. This bit of code, I think, is the main picture we looked at last Friday. Yep, there it is. So what's going on here? Again, you've got the xy plane is the domain. That's down at the bottom of the box. Again, remember the positive x-axis goes to the right, and the positive y-axis goes into the screen. The graph of the function itself is the surface that looks about like this. And we're cutting that surface with vertical planes. Two vertical planes that are parallel to the x-axis, that are at constant values of y. And one vertical plane that's parallel to the y-axis that's at a constant value of x. Those planes are going to intersect the surface along curves, and those curves can be thought of as parametric curves. I use parametric plot to make them here. But they can also be thought of as graphs of functions of x and y individually, whose slopes can be interpreted in terms of those partial derivatives. Let's take a look at one of these here. So for example, the one that's colored red comes from this parametric plot code. You should make sure you think about why this works. So this, I'm using parametric plot 3D. This is a parametric curve. X is the parameter, and that makes sense because that's parallel to the x-axis. Y is fixed at -1. This plane right here is at y equals -1. So x is x, y is -1, and then you can take that point and plug it into the function to get the z coordinate. And you let x vary from -5 to 5. It's colored red. You can see it's that one right there. We can take that function and make a regular plot of it. First of all, it does have a formula. It's got to be a cubic. There it is. And we can make a regular plot of that. Okay? So this is the same function, essentially, that as the red curve right there. To make it look a little bit more accurate compared to this graph up at the top, we can change the plot range to being 0 to 400 down here. And now you can see it looks a little bit more shaped like the red graph does. We do the same thing for a different value of y. I think this other value of y with the blue curve, that's y equals 2. So I can find f of x comma 2, again a regular function of x, because I've set y equal to 2. I can plot that. Doesn't look much different. It actually is different, and we can see that if we put the plot inside of manipulate. We're plotting these as functions of x, but you get different functions for different values of y. So we're seeing an animation that changes as y changes. Different values of y give you different cubic functions here. And they're all related to the three-dimensional graph. In fact, let's just copy and paste this stuff and put it inside of the manipulate too. Put it down here. Let's see, I'd like to make y the animation parameter, except I won't call it y, since I've got lots of y's in there. I'll call it b. B is going to go from -5 to 5, so I'm embedding all this inside of manipulate. What is my goal here? My goal is to see the one plane whose intersection with the surface is colored red. I want to see that move as b changes. I need to make that -1 a b, and I need to make these two -1s b's as well. That's going to correspond to the red curve. We've got a b, make this a b, and this a b. B is now the animation parameter that I can see there. And as it changes, you can see the intersection changing. It doesn't seem to change very much, but it does change some. What you're seeing here in this three-dimensional picture as b increases is you're seeing the exact same kind of thing going on here. Because when you look at this graph, you are essentially looking at those intersections. And then, what does the partial derivative tell you there? It tells you the rate of change in the x direction. For the red and the blue graph, y is fixed. So you're going to want to interpret the partial derivative with respect to x as telling you the slopes of these graphs. What can I do now with directional derivatives, however? I can modify this to make a similar kind of graph where I intersect the surface not with a plane parallel to the x or y planes, but parallel to some other line. Let's draw a picture here. So this is the xy plane. I got some point, P, whose coordinates are A, B. I'd like to interpret the meaning of the directional derivative of the function at this point in some direction. Let's draw the direction this way. There's a unit vector u, whose components I'm calling C and D. Essentially what I want to do is I want to cut the surface with a plane perpendicular to the xy plane, and it's going to cut the xy plane right along that line. What you have to do when I draw this on the board is you have to imagine the graph of the function in 3 dimensions being in front of the board. You want to imagine the xy plane is the board, and the z-axis comes out of the board, like this. Then your graph that we've been drawing, looking at it in the ordinary way, would be in front of the board. And to see it in the way we've been looking at it, you'd have to kind of turn your head sideways. Well, and look at it like this. If you were looking at it from Mathematicus perspective, I'd have to be up here and look at it sort of downward to look at it more with the perspective I usually draw it. You're slicing, you're taking a plane perpendicular to the xy plane, and you're slicing the graph of the function so that when it hits the xy plane, it's matching where that line is. And that intersection and the slope, the rate of change of that intersection on the graph that's now sort of, going to look at it sideways here, is the thing we're trying to measure with this directional derivative. I can try to get this plane in here a couple of ways. I could think of it in terms of a regular slope, point slope form equation. Y equals m times x minus a plus b. Or I could think of it in terms of the u. I'm going to go ahead and think of it in terms of the this equation here, and then show you how to figure out what the u should be after we get the animation going. So let's see. I'll go ahead and copy and paste this code, but modify it. We can get rid of a lot of these contour plots. We just need one of them, in fact. Contour plot 3D. What do I want? I want to draw the plane that I'm going to cut the surface with. In 3 dimensions, it's going to still have the equation y equals m times x minus a plus b. B is now no longer going to be the y coordinate of the plane. Instead, it's going to be, in that graph up there, it's going to be the second coordinate of the point it's going through. M is going to be the slope. M, A, and B are all going to be animation parameters. In fact, let's start them all out at 0. Here's the syntax for how you start them all out at 0. And go between -5 and 5. What else do we want to change? So we only have that one contour plot, and that will draw a plane perpendicular to the xy plane, because you don't see a z in the equation, so z can be anything. So it's going to be all the points in 3-dimensional space whose xy coordinates lie on this line, and you project them onto the xy plane. The z coordinate can be anything. So that's going to generate a plane perpendicular to the xy plane. What about the curve of intersection? Let's get rid of these other two here and just do the one that's red. Well, one way I can parameterize it is, again, using x as a parameter. And the first coordinate of this parametric plot will be x then. The second coordinate is going to be m times x minus a plus b. And the third coordinate comes from plugging those two values into the function. So it's going to be f of x comma m times x minus a plus b. So again, m, a, and b are going to be fixed when this makes this plot. X will be the parameter here. It's going to be the parameter for the parametric plot. This will trace out a curve for specific m, a, and b, but then M, A, and B can be changed because they're the animation parameters. So I think this is going to do what we want it to do. Okay, here's the initial picture. M, A, and B are all 0. If I change M, I change the angle, the slope of the line of projection, which you can get by looking straight down, by the way. And I can change A and B as well. If I change A, move it to the right. Change B. Well, that looks like it's going to the left. It's actually better to think that it's going into the screen. Actually, it's probably good to put the point itself in here as well. Do that with list point plot 3D A comma B comma F of A comma B. We'll plot the point in question. Let's see. Not as big as I was hoping. You can see it there. I'm not sure why it's not overriding the. We don't see it sort of on top of the red curve. Let me make it bigger. There's the point. Again, we can move it to the right or left by moving A. We can move it into the screen or towards you by moving B. We can change the slope of the curve that is going through it by changing M. Let's pick some specific values and confirm the meaning of the directional derivative. So let's pick M to be 2, A to be 2, and B to be 1, say. What is the meaning of the directional derivative at this point in the specified direction? The point is 2, 1. If I'm going to use the formula that you see here, I've got to find the gradient vector at 2, 1. I also have to figure out this unit vector u. Not too hard to do if you look at the picture here. Let's draw, well, okay, I guess I can think of this as the point 2, 1. It looks pretty accurate. If m is 2 here, u is going to be in the direction of what vector? This slope is 2. What's a simple vector that's in that direction? Don't worry about whether it's a unit vector. One, 2 is going to be in that direction. The length of that vector is square root of 5, so if you divide by square root of 5, you're going to get a unit vector in that direction. So according to this formula, I guess we need the gradient too. And back to that other function, not the function that we used earlier today. Oh, I forgot what it was, x cubed. X cubed plus x times y squared plus 3y minus 10x plus 250. Partial derivatives are 3x squared plus y squared minus 10 and 2xy plus 3. So the gradient vector, nabla f, or del f, the gradient of f, has got components equal to these functions. It itself then is a function. It's a vector value function. Such functions are typically called vector fields, and we will be talking about vector fields. What about at the point in question, at the point 2, 1? X is 2, y is 1. What will we get? This might be a different point than I did in the last class because it these numbers are coming out differently. So x is 2, you're going to get 2 squared is 4, times 3 is 12, plus 1 is 13. And then plug the point in there. I'll get 2 times 2 times 1 is 4, plus 3 is 7. Does that look right? This is a different thing than I got in the last class. I thought it was the same function at the same point. Okay, yeah, thanks, that's it. Okay, so that's the gradient vector at that point. Let's do this dot product. So the directional derivative at the point in question is going to be the dot product of 3, 7 with 1 over root 5, comma 2 over root 5. That'll be 3 over root 5 plus 14 over root 5. That'll be 17 over root 5. Which will be between, what, 6 and 8.5, somewhere between those. How do you interpret the meaning of this? What does it mean? It is a directional derivative. It is a rate of change. It can be thought of as a slope, though you do have to be careful, especially if you do it the way I did, where I made m the slope of that line, the animation parameter, and I used x as the parameter for the parametric curve. That's actually not ideal, not an ideal way to think about it for interpreting the meaning of the directional derivative. The reason being is that small changes in x can produce relatively large changes in the distance traveled along that line if the slope is large. So you want a parameter that's going to cause a motion by 1 unit in distance as you let 1 unit of time go by, effectively, a unit speed parameterization. I can do that, let's see, by making a modification here. With my parametric plot 3D, I can do a different parameterization. What one should I do? How are we doing on time here? About 10 minutes left. Okay, what should I do here instead? I want to use U, really. Come up with a parameterization that uses U. I can draw the position vector going from the origin to P, call it OP, and then add that vector to T times U, where T is now going to be the parameter for the parametric curve. OP plus TU, where U is a unit vector, is going to be a unit speed or arc length parameterization of that line there. I think I'm not going to manipulate it. I'm just going to make it a specific one here. Make it simpler. So we'll get rid of the animation, get rid of the M, B, and M, A, and B. Get rid of the manipulate. Make the A and B 2 and 1. And use a different parameterization here. Effectively, the position vector has components that are the same as the coordinates of P, 2, 1. Add on T times U. U can be thought of as 1, 2 divided by square root of 5. Let T vary now. I actually can let it vary near 0. I don't have to go -5 to 5, but I could. It wouldn't hurt. It's probably not going to draw the entire curve. Do this. Let's see what it looks like. Oh, I need to get rid of. Make M2 here, A2, and B1. And where did the redness go? Oh, I know what's wrong. That's because I need a third coordinate. So you need to plug all this into F as well. Which means I'm also going to need to change the formula for F in a certain way. Let's see, no, this is not quite right. Let's see. That's going to be third coordinate. Maybe I better do it just coordinate by coordinate. If you think about coordinate by coordinate, this is going to be A plus TC, comma, B plus TD. A plus TC plus, comma, B plus TD. So A is 2, B is 1. So I've got this to start with. I want to add the first component, A plus T times C. C is, again, 1 over root 5, so I'm going to have T over root 5. That's the first component. That's A plus T times C. What about B plus T times D? B again is 1. D is 2 over root 5, so I'm going to have a 2T over the square root of 5. What about the third coordinate here? Now I need to plug these things into F. So I have F of this first thing. Comma F of the second thing, which I just changed the 2 to a 1 and put a 2 in front of the T there. That should do it. There we go. Okay. If you felt confused, okay, that's worth watching the video online here perhaps if you felt confused if I went too fast there. Essentially, again, I'm just writing it in terms of components and adding a Z component. Make sure it's on the graph. And the directional derivative is going to measure the slope of this graph, 0.21. And we thought it was being under that black dot. What's the rate of change in that direction? What's the slope of the graph in that direction?
What's T?
T is just another parameter. It's just, I picked T, I could have picked something else. I'm just trying to parameterize the curve, that's all. And T is a typical parameter that we pick. So yeah, any letter other than X or Y, we can find there. I mean, I could even use X and Y as well, but just conceptually, we're thinking of X and Y as being something different. Is that truly the right slope? How could you tell? You can make another plot and calculate another derivative to make sure it's the right slope. We could make a regular plot, in fact, of this function right here, near t equals 0, because t equals 0 is going to put you at p when t is 0. If I make a regular plot of this function of t, the slope of that function of t at t equals 0 should match the directional derivative of this original function at this point p in that direction. Because essentially I'm taking this red graph and it's like I'm grabbing it and drawing it in a regular coordinate system when I do this. So let me copy and paste this function down here. T just needs to be near 0. I could do it from -5 to 5. The real key is what's the slope at 0? It should equal the answer, 17 over root 5 for the directional derivative. The slope of this function is 0. Essentially what I'm doing again here is I'm taking that red graph, the intersection area, it's like I'm grabbing it and plotting it in a regular coordinate system. How can I confirm the slope is right? I can use the derivative. Actually, let's go ahead and look at what the formula for this thing is. It's probably going to be kind of messy. The formula for this thing is kind of messy. You could try to simplify it with maybe by expanding it. And I'm not sure why it's not combining these two t terms. I think if you add the coefficients of those, I think it confirms our answer. You get a common denominator here of square root of 5. This is going to be 5 over square root of 5. 5 plus 12 is 17. You're going to get 17 over square root of 5. That's the coefficient of t, and that will be the derivative of this thing at t equals 0. I'm going to expand it. Why is it not combining those things? Maybe if I just simplify. There we go, 17 over 5. And that is the derivative of this thing. At t equals 0, there's the derivative with respect to t. Plug in t equals 0, you get this, which does simplify to that. It is matching this answer. But the main thing that you want to get here is the idea. Why did that work? Let me review what I did again. Okay, so again, the xy plane is the bottom of the box. The x-axis is going to the right, the y-axis is going to the screen. The point 2,1 is underneath this black dot in the xy plane. It's the bottom of the box. U was pointing in the direction of 1, 2. It was a unit vector right here. We're trying to find the rate of change of this function, of this intersection really, in that direction. It's going to correspond to the slope of the red curve at that point in that direction. What I did was I imagined grabbing that thing and graphing it with a regular graph. I don't know that you can tell that that is right there. You can see it sort of looks the same. We plotted this over a bigger range of values of t. You can see more of the graph. Hard to tell that that's perfect, but it evidently is matching what you see here. I suppose if I change the plot range, it might look like it matches better. Yeah, if I went negative 10 to 10. Well, I don't think we're seeing the entire graph up top there. Yeah, we're not. Like I grabbed that red graph and I put it in this new plane, this TZ plane. The slope at 0 is going to be the same as the slope as this one at the black dot. That's what I confirmed. Okay, so all these different derivatives, the regular partial derivatives and the directional derivatives, can be thought of in terms of slicing graphs. And that's the main conceptual point that you want to realize. And then the calculational point. This. Give me 30 seconds to show you one more thing. Maybe it'll be a minute. We got a minute left. Another thing you're going to want to do with gradients. Let's make a contour plot actually. Another thing you're going to want to do with gradients is you're going to want to plot them as a vector field. What does that mean? Well, you make it with Mathematica with something called a vector plot. The syntax looks like this. Actually, we need fx. We need those partial derivatives in here. Let's add more contours. You're plotting a bunch of gradient vectors. These arrows are, well, they're scaled down. They're shorter than they should be, because if they were the right length, it would make the graph look really messy. All these are essentially gradient vectors scaled down by a certain factor. And there's a very nice relationship between these vectors and the level curves here. For one thing, you can see that they're all perpendicular to the level curves, and they're all pointing from dark to light. And that's going to be fundamental for us to realize and to understand this better. Okay? So look for that in your reading. See you on Wednesday.